Welcome to this lesson on constants in preprocessor directives. In this lesson, you'll learn how to create constants, values that don't change, but assign meaningful name to the constants to make your programs more readable, and they'll make your programs more flexible, meaning they'll make it easier to make changes to your programs, because rather than having to search through your programs for different constant values, you can just refer to the name, and the C compiler will associate the corresponding definition you've given it. We'll also take a look at the include statement, which you've been using in all your programs so far to include standard IO.h, and its role in the pre-processing process. When you compile a program, before the compiler actually starts, a second program called the C preprocessor runs, and it will process all the constant definitions that you create. It will process the contents of the header files that we include, such as standard IO.h. And so it allows us to do some things before the compilation actually starts, which gives us great flexibility. So let's go ahead and jump in and get started. So you've already been using one preprocessor directive, the # include. Before the compiler runs, the preprocessor runs, and it looks for directives such as include. In this case, when it finds include standard IO.h, it will go open that file and include its contents within your program, just as if you had typed them all in yourself. And so standard IO.h contains a lot of key definitions and function prototypes that our programs use. And so if we, in the second program, try to run the program and compile the program without including standard IO.h, the compiler won't find the definition for printf. It's defined in standard IO.h. And so if we run this program or try to compile it, we're going to get an error message from the compiler that says, I didn't find the declaration for printf. And so it gave us a warning. And so it still ran our program. We still see the output, hello world. But if we want to correct the error, we just include standard IO.h at the top of the program. The preprocessor will include that file's contents. The compiler will then find the definition of printf, and our warning message will go away. So you can use preprocessor directives, specifically the # define directive, to create constants that have a meaningful name to use in your program. Let's take a look at this first program. It's including standard IO.h, so we have the definition of printf. But it's in declaring a variable called pet. It's assigning that variable the value 1. It turns out that the program uses the value 1 for dogs and the value 0 for cats. And so we have an if statement and says, if pet is equal to 1, print the message, dogs are great. Otherwise, print a message, cats are great. And so our program works, and using the value 1 works, but it's not as readable as a program can be. And so instead, we'll take a look at how we can define constants to improve its readability. So when we define a constant, we use the # define compiler preprocessor directive. In this case, we're using define to create a name, dog, and we're assigning it to value 1. You'll see that the word dog is in all uppercase. Typically, C programmers, when they define constants, will use uppercase letters to distinguish constants from variable names. And so in this case, we've just created a name that has the value 1 called dog. We've then used # define to create a name, cat, that has the value 0. Note that there's no equal sign, so we don't do an assignment. When we define a constant, we just specify the value. When we later compile the program, the C preprocessor is going to find our constants, in this case, dog and cat, and it's going to look through our program for any use of those constant names. And so when it finds that first assignment operator, int pet equals dog, behind the scenes, the preprocessor is going to put the value 1 in there. When it finds the second reference, if pet equals dog, behind the scenes, the preprocessor is going to put the value 1 in there. It's going to do a direct substitution. But our program code is more readable because we can say, oh, we've assigned pet a dog. Oh, we're testing to see if pet is a dog. So the readability of our program improves Behind the scenes, however, the preprocessor has put those constant values in place for each time they occur. You've learned that an array is a variable that allows us to store multiple values of the same type. And a character string is just simply an array of type char. When we define an array, we have to specify the size of the array. And so typically we'll use that size to define the array size when we declare the variable. And we'll also use it later in loops where we're starting to loop through all the elements of the array. And so in this case, we're using the #define directive to create a constant, it's in uppercase, called buffer_size. And we're assigning it to value 128. Again, there's no equal sign. We're just specifying the value that we want associated with that name. Within our main program, we create a character array called title based on that constant. So we're creating an array that's 128 characters long. But in this case, it's improving our readability. But later, if we want to loop through the array, we need to know the number of characters in the array. We can use that buffer size constant again. And so if we run this program, you can see that it's displayed our output as we've desired. And so our constants or definitions are only used during the preprocessor stage, but they allow our programs to be more readable. It turns out that the C compiler defines several constants for us. And one of them is the __file__ constant. And the C compiler assigns to it the name of the file that we're currently compiling, the name of the source code file. And so in this case, if we run this program, we'll see that behind the scenes, this file is located in the temp directory, and you can see its name with the .c extension. This becomes useful as your programs become larger and you're breaking them into different source code files and then later compiling your whole program. You may want to display a more meaningful message that says specifically which program file are you compiling. And to do that, you can take advantage of this predefined __file__ constant. And so we'll learn next that there's other preprocessor predefined constants that we can use to help us display similar messages. The C compiler also defines an __line__ constant. And again, it's all in uppercase. Our constants are typically always going to appear in uppercase if we're following good practices. And so in this case, we've got a program that's going to loop from 0 to 9, displaying the value of our loop. And if that value is odd, it's going to display as an odd value. If the value is even, it's going to display a message that says the value's even. But it's going to also use that _line preprocessor constant to tell us, hey, we're about to start the loop. We're at line X. Then we're going to do our loop. Let's take a look at the loop for a minute. Within the loop, we're just going through the values 0 through 9, and we're taking a look at each value. And we're using the C modulo operator, which gives us the remainder of an integer division. For even numbers, if we divide that number by 2, we're always going to get the result 0. For odd numbers, if we divide that number by 2, we're going to always have a remainder 1. And so our code is looking at that result, and if it's equal to 1, it's saying, hey, this is an odd number. Otherwise, it's saying this is an even number. So the loop is kind of fun. But after the loop ends, the program will say the loop is ended and we're at line X. So let's go ahead and run our program and look at the output. And so sure enough, we see the message. We're about to start the loop at line 7. Then we display our values even, odd, even, odd, even, odd. And then when the loop ends, we say, hey, we've gotten to the end of the loop at line 15. Now, sometimes when you're trying to debug a program, trying to remove the bugs from a program, you can't tell where your program's breaking, which line number within your source file. And so you can use the _line constant to say, hey, I've gotten this far, everything's working, or I've gotten this far and it just broke, to help you find your errors within your program. Now you've learned that C predefines the underscore, underscore file, underscore, underscore, and the underscore, underscore line, underscore, underscore constants for us that we can use in our programs. It turns out that the compiler also lets us assign values to those. And so in this case, you can see that within main, we're using the # preprocessor directive with line to display that we're at line 100 in the file demo.c. And so we can set those values. And so it's the same program. We're going to look at even and odd values, but we're just wanting to show the ability to assign the line number and assign the source code file that those constants use. And so let's go ahead and run this program. And so it says, hey, I'm in demo C and I'm about to start the loop at line 103. And so in this case, we don't have 103 lines in our program, but we've managed to show how we could redefine those processor directives to make them more meaningful as we're trying to debug our source code. When we create large projects, we may have multiple programmers working on source code, and they're checking those their files into a source code repository. And maybe one has worked on a program most of the day but didn't quite finish and is left for the day. But before they do, they've uploaded their code and they want to leave a message that just says, hey, I'm not yet done. There's a bug that I'm trying to fix. So when somebody comes in and tries to compile this code, they're going to be aware of the fact that there's a bug because the code's going to generate a syntax error. To do that, we're using the #error preprocessor directive, and we've got a message that just says code is not complete, still has a bug. And you can see, sure enough, if we look at our for loop, it's left out the initialization part of the loop. And so we maybe have a potential where we wish that we'd assigned count a different value. We're still working through solving that. So let's tell others that, hey, there may be a problem here. Let's run this program and see what happens. So when the compiler runs, the preprocessor will run first and plug in code that causes the compilation to stop. And it's going to display that message. And sure enough, you can see that the compiler encountered a # error. It displayed the message, code is not complete, still has a bug. And so, again, this gives us finer control over how our programs get compiled. We don't use the # error that often, but you may see it in older programs that you are looking at. Again, when you're working on a big project, the program, you might work on it for weeks, months, or even years, and you may want to know when was the last time this program was compiled. And we can do that by using some predefined constants. The compiler will plug in the current date in the _ date constant and the current time in the _ time constant. And so we can use those maybe until we're getting ready to release our program to production. We always want to display, hey, here's the last time this thing was compiled. It's a big project, everybody's working on it, people are compiling it. Which version of the program am I running? So let's run this code. And you can see, sure enough, it displays the current date and current time that the compiler last ran. Now, different compilers will predefine different constants for us. And you need to look at your compiler documentation to see which constants it might define. But one that's typically defined is the _stdc constant that says the compiler is ANSI C compliant. And so we can use the if-def preprocessor directive to check to see, hey, is this constant defined? And if it is, we can do something, and if it isn't, we can do something else. And so in this program, we're including standard IO.h. We've got our typical main, but within the program, we're using # if-def to say, hey, is this constant, has it been defined by the compiler, has it been defined by another programmer? And so if it's defined, I want to do something. In this case, I want to print the message, yes, this compiler is ANSI C compliant. And if it's not, we want to display a message so stating. When else might you use this? assume that you've got a lot of programmers working on a project, and so different people are writing different source codes. Different people might be defining different constants, and you want to use a constant called big. But before you create that constant, you maybe want to check to see, hey, has anybody else defined this constant? And if they have, maybe you won't define it, and you'll pick a different name. If they have, you'll do something else. And so using the #if-def, you have this functionality. Let's go ahead and run this program and see what we have. And so sure enough, this program is ANSI-C compliant. And so the SD or STDC constant was defined by the compiler to say, yes, I am. In another course, we talked about the C++ programming language, and it turns out that we can write programs that look pretty much like C and compile them using a C++ compiler. So maybe we want to know, are we using a C compiler or are we using a C++ compiler? And we can take functions that were written in C and still run them in C++. So we want to test for the compiler type. And a lot of compilers will define the __ C++ constant. Would have preferred to see it in uppercase just to be following our good practices of always putting our constants in uppercase. But in this case, let's go ahead and run this program and see what we have. The constant's not defined, and so our if-def statement isn't true, so we don't display the C++ compiler, but instead we do the else portion, the #else, which says, hey, this is a C compiler. And that makes sense because I'm running a C compiler right now as opposed to a C++ compiler. So we talked about the fact that with a large programming project, multiple programmers may be working on different source code files. Multiple programmers may be defining their own constants. And when that happens, we could redefine possibly a function that was created by somebody else, which causes our program to break. And so in our first program, you can see that we're defining a constant called big. It has the value 10. Uppercase letters, good job following best practices. Within our code, we have another # defined that changes big's value from 10 to 100. And so we're redefining a constant that already exists. That could be problematic if we make something smaller. Now our buffer's too small. We end up with a buffer overflow, or our loop stops working because we've changed our constant size. And so when we compile this program, the C compiler will tell us, hey, you just tried to redefine big. It gave us a warning. It didn't stop the compilation, so we still got an executable. When you get compiler warnings, it's normally a sign that you should stop for a minute and fix whatever code is causing the warning, because that's an indicator that it may lead to problems down the road. But that said, our program still ran. And so to avoid this error, we can undefine a constant, which could be bad in and of itself as well, but we'll at least get rid of the compiler warning. So you can see that this program again uses #define to define the constant big with the value 10. But within void, we're going to make it even bigger, and so we're going to assign it the value 100. But before we do, we undefine the constant. Now that's going to solve our problem for this program. It might not solve our problem, or it might make problems if we undefine one that we didn't define initially. But let's go ahead and run this program. And you can see it loops through the values from count equals 0 to count being 99. And it's just a simple for loop. And it's based on our constant. And so what's happened here, as we look at our code again, when the preprocessor runs, it's going to do a lot of this for us. It's going to include standard.io.h, so it pulls that source code into our program. It's going to define the constant big, so anytime it's encounters big, it's wanting to use the value 10. But later it encounters that #undef and says, okay, I need to undefine big. I don't have a value for it anymore. But immediately following it, it encounters its new value with the #define big. All this is going on within the preprocessor. So depending on the compiler you're using, it may have some directives that allows you to use. Maybe there's a directive that suppresses warning messages or makes warning messages more complete. And we call those compiler directives pragmas. And so the pragma preprocessor directive allows us to specify values for those. The pragmas are all going to be compiler specific. So if you're using one compiler, it may have a set of pragmas that it supports. A different compiler may have a different set. But you're going to hear, as you're talking to more experienced programmers, they may talk about compiler pragmas. The compiler pragma is just a directive that we're giving to the compiler when it runs. So kind of some options or some setting values. And again, it's going to be dependent on the compiler you're using. So we've learned that when the preprocessor encounters a #define directive, it's going to take the name that we're creating, and every time it encounters that name within your code, it's going to substitute in the corresponding value. We've done that so far using #define to create constants. We can also use #define to create something called a macro. And so you can think of a macro as code we want to substitute in. And so in this case, we're using #define to create a macro called square. Our macro gets a parameter, x, and it has the value of x times x. And so within our code, within our for loop, you can see that we're looping through the values 1 through 10, and we're displaying the value and its square. To calculate the square, we're using our macro. And so when the C preprocessor encounters the square count in our loop, in the printf statement, it's going to substitute in its place the code that we've defined. And so you can see our code is take the value of x and multiply it by x. So we're going to get the square. And so it's important to note that up in our macro definition, we've got our code, but we don't have a semicolon, because if we had a semicolon at the end of it, that would become part of the substitution. And it would stick the x times x semicolon right in the middle of the printf statement, which would cause a syntax error. Let's go ahead and run this code. And you can see, sure enough, it loops through the values 1 through 10, displaying the value and its square. And so macros allow us to create more readable code. And so rather than having x times x within our for loop, we can use the macro name instead, which is more readable. And we'll see that we can define macros to do a lot of functions. We could get the absolute value, we could do the cube, we could do a variety of processing, and we'll take a look at some examples in a minute. When you use macros, you need to be careful. You need to think through the substitution that's going to occur. And so let's take a look at a macro gone bad, an error that happens. So we've got our #include, standard.io.h, we understand that directive. We've got our #define, and we're creating a macro called square that gets a parameter. And in this case, it's doing x times x. And that would seem like that makes sense. Every time the preprocessor encounters the square within our code, it's going to substitute in directly the code that's given. And so we're going to substitute in x times x. And boy, that sure seems like it makes a lot of sense. And let's go ahead and run the program and see the problem. You can see that the code should display the square of the value 5. And then it should call it with the square of 3 plus 2, which is the value 5. And so when we run this program, we would expect to see 5 squared is 25 and 3 plus 2 squared is 25. But when we run the program, we see that 5 squared is 25, but 3 plus 2 squared is 11. And that's because it's doing a direct substitution. And so let's take a look at what's actually happening with those substitutions. When we say printf, 5 squared is %d square 5, the preprocessor is going to put in our x times x, or our 5 times 5 in that place. And sure enough, that works. The problem occurs when we do the square 3 plus 2. And so when we look at what the preprocessor has done, it's created x times x. That was what we told it to do. So 3 plus 2 times 3 plus 2. But if we remember our C operator precedence, multiplication has a higher precedence than addition. So what actually gets executed is 3 plus 2 times 3, or 6, plus 2. That's what's giving us the 11. The way that we correct this error is to come back up in our macro and say, we want square to be defined as x times x, but with parentheses around each x to force it to be evaluated first before it does the multiplication. And so if we make that change and run our program, we see that 5 squared is 25 and 3 plus 2 squared is 25. Everything's working again. But you need to be careful with macros. And we talked about the fact that if we would have included a semicolon at the end of our macro definition, the preprocessor would substitute in that semicolon, which may cause a syntax error. So the rule of thumb is if you're doing any kind of arithmetic operations with a macro, group your x value in parentheses to force the operations to occur with the correct precedence. So let's take a look at a couple other simple macros. We've got a min macro, we've got max, we've got a sum, we've got a cube, and you can see how they make our code pretty readable in main. But you should take time to look at what's going to be substituted. And again, you see I've got the comment there that says no semicolons because we don't want to substitute in the semicolon. But you can see our macros in a couple cases get 2 parameters. So min gets x and y. It's the 2 values that we want to compare and return the minimum value of. Max gets x and y, 2 values we want to compare. Sum gets x and y, 2 values that we want to add. But you can see in the code that the macro is going to substitute, I've grouped those parameters within parentheses. So if we pass expressions to them as opposed to values, the expressions will be calculated first before we apply the macro substitution. And so if we go ahead and run this program, the minimum of 5 and 3 is 3. Yep. The maximum of 7 and 6 is 7. That looks good. The cube of 9 is 729. Cube of 10 is 1000. The sum of 9 and 8 is 17. Yep, it looks like all of our substitutions are working. So take some time to experiment with these. You could go back and create them again yourself, but without the parentheses around the parameter values, and see the errors that can occur. And so macros are very convenient. They help our code become readable. You just need to be careful as you're using them. So in C, we'll break our programs into functions, smaller pieces of code that perform meaningful tasks, and functions will often return a value. They'll perform some kind of calculation, return the result. And functions have to return a value of a specific type. If we're adding integer values, we return an integer value. If we're working with floating point values, we return a floating point value. But macros are typeless because there's no return value. We're just doing the substitution. And so in this case, we're defining a macro called cube. It's getting a parameter called x. You can see it's just x times x times x, but I've used parentheses in case we pass an expression to it. And so our macro substitution will be correct. In the first case within main, we're printing the cube of 9, and so it's an integer value. In the second case, we're printing the cube of 7.7. We're not calling a function, so there's no type involved. So macros are typeless, so we can use the same macro for integer values or floating point values. So what are we going to learn next? As you've learned, programs store data in variables as they run. A variable normally stores one value of a specific type, such as value type int, value type float. Often, however, our programs must work with multiple values of the same type, such as a class's test scores, a list of product prices, and so on. An array is a data structure that stores multiple values of the same type. And so in our simple code example, we're creating an integer array. We proceed with the int type. our array name is array, it's going to store 5 values. And we've initialized those values to 10, 20, 30, 40, and 50. In the next lesson, we'll learn how to create arrays of all types: character string arrays, floating point arrays, integer arrays, arrays of different sizes. And we'll learn how to manipulate those arrays, assign values to them, display the values they contain, add values to each one of the values in the array. And so we're going to do array operations. So let's go ahead and get ready to get started.